We had a super elevation question that happened just recently, and I kind of want to go over what we determined on that question. The question dealt with the total number of lanes applied to the super elevation and the multi-lane factors. And so here's the data that the person was asking the question about. And if we look at the super elevation report on this section, you'll see that in the report that we have number lanes 4. Our design speed is 60 miles per hour with an Emax of 8%. And if we look at the curve that we have out here, it's a 3,000 foot radius curve, and we get a application length of 133. Now if we look at our charts, our standard plans, you'll see that for a 3,000 foot radius, what you normally do is you always be conservative and you go to the higher super elevation rate. And so in this case, for a 3,000, we would use an E% or Emax of 5% for this super elevation rate. But what we should be getting for 4-lane is a runoff length of 200 and not 133, which if we look back at the Geopack report, you'll see that we do have the 5% Emax, but we're getting 133 and not 200. And so that led us to look at the data a little bit deeper, or the actual files. And the first thing I did is, instead of running this super elevation, I'm going to recalculate it using 2-lane just to see if I get a different result between 4-lane and 2-lane. And so I went in to calculate super elevation. I picked my standard file table, which is the English 2011. It's based off the 2000 AASHTO Green Book. There's my 8%, 60 miles per hour, all cases. Design speed 60, linear. This time the number of lanes I'm going to put in there as 2. And undivided. And I'm going to say no to open the editor. It's going to recalculate. And so when I recalculate it, I'm going to open up the report again and look at my data here. This time I got number of lanes 2 and everything else is the same, and for whatever reason I'm still getting 133. So again, I'm going to go back to the microstation data and start taking a look at what we got here. And when I click on the super elevation section, you can actually zoom in and see how the shapes are built. In this case, all I have is actually 2 kind of lanes out here, 2 12-foot lanes. And so since it's a 4-lane super elevation that we're trying to apply, what I decided to do is I was going to make these lanes wider, because if you look in the super elevation SEP file, there is a nominal width lane, and that's set to 9 feet. And so that considers a lane width of 9 feet to be a full lane width. And so since these are only 12, you can only get 1 lane in this area here. So I thought, well, let's make the lanes a little bit wider and see if that nominal lane width has an effect. And so I did that in another file, which I'll open up real quick here. And it looks the same, but if you click on the super elevation shape in this file and zoom in, you'll see that I got 24-foot wide lanes. And so that nominal lane width, if it does work, we'll see that there's at least 2 lanes on this side of the center line and 2 on that. And so what I'm going to do now is come in here and go ahead and run this, or calculate the super elevation one more time. I will go ahead and go with the 2011 AASHTO. All these the same, and then I'm going to do number of lanes 4, and undivided. Okay. Once that's calculated, I'm going to go ahead and open up the report again. I've got my number of lanes to be 4, design speed 60, and if I look down here, 5% perfect for Emax, but we're still getting 133. So the lane width, the width of the lane doesn't seem to make any difference, and it's not looking at that nominal lane width. And so what I did then is I went back and I created another superelevation file. You could do it all in the same, but just for speed's sake, I created another one. This time I did a 4-lane undivided, and in this one, if we look at it, once it opens up, I'm going to click on the shape or the section. I'm going to go in there, and you can see now that I've got two 12-foot lanes on this side of the center line and two 12-foot lanes on that side of the center line. And this time I'm going to go ahead and run the superelevation or calculate the superelevation one more time. Same values as before. And now if I look at the report once again, you'll see that I got, again, 4 lanes, 8% Emax of 8 and 60 miles per hour. Now if I go down here below, you'll see now my application length, which is really my runoff length, is 200. And so with superelevation, the lane width really doesn't have any effect on it. It's the actual number of lanes that are visible to the program out there. So if you want 4 lanes, you actually got to draw 4 lanes. If it's a 3-lane, you can have to draw 3 lanes. And so the next part of this presentation is going to talk about where these numbers come from, the lane width and the Emax and stuff like that. So we're going to go into that next. And I'm actually going to start back at the beginning of my superelevation show here and kind of go over some generic superelevation settings. And so here we've got a diagram that kind of shows you all the sections of superelevation. You can see the cars at the AA section. It's the last section before it starts to rotate. And then when you go to the BB section, you can see that the one side is going up to 0%. The CC section is where it's 2% across the entire roadway. Then it goes down to the DD section, which is full super, and then it stays full super through the rest of the through the curve, and then it does the reverse, going from the DD down to AA section. So again, DD's full super, then we're going back down to a 2% super. Then the BB section is back down to a 0% super on the one side, and then the AA is back to a 2% on both sides of the center line. And then it remains at 2% the rest of the tangent section of the roadway until you introduce another curve. Okay? So those are the critical sections of the superelevation. Now in the next slide we have a picture of our standard plans, and you can see the AA section, the BB section, CC and DD, and they kind of summarize the same thing that we just showed you on the previous slide. And we're going to kind of focus on this part of this detail of this sheet. If we blow that up, you'll see that we got all the sections in here, and the most important part or point of this diagram is this dot right here, which is the PC or PT point of the curve. Now this is for a non-spiraled curve, this sheet. And so if you know where the PC is and you know your runoff length L, you can calculate pretty much every other location on this diagram. And so to go from the PC or PT, if you know L over 3, which is L is the runoff length, and divide that by 3, you can get to your DD section, which is full super. And then if you go from your DD section down this length, you'll know where your BB section is, which is the section where it's 2% on one side and flat slope on the other. And then if you can calculate your X value, which your X value is just your runoff length times your normal crown in percent divided by your E rate on your curve. And if you know that X value, you can calculate your CC section, which is the 2% full super. And then you can go back an X value to calculate your AA section, which is where you have a normal crown, 2% on both sides of your pivot point. And so we use this dialog to calculate our superelevation. And the number of lanes, again, the number of lanes, if you have a value typed in here, you want to have the number of lanes created in your superelevation file, the exact same amount of lanes. Okay, and if we look at the 8% 60 miles per hour, between those values, we can look at our standard plans. In this case, we had 60 miles per hour. We had a 3,000 foot curve. And when you have a number that's in between these two values, you always go with the more conservative value, which would be a higher superelevation rate. And so in that case, for a 3,000 foot radius, you'd use a 5% Emax or 5% max super. Now, the file that we use to calculate our superelevation is this English 2011 SEP file. This SEP file has been around for quite some time. It actually was probably the SEP has probably been around for at least 20 years or so. And if we look at the file where it's stored out on our MoDOT workspace, GPK standards in the Superelevation folder. And you can go out there and look at that file if you want. You can't modify it because it's read-only. But if you open it up, it'll look something like this. And this is just a partial screen capture of the entire file. You can scroll down here and see a lot more. But it's basically broke up into sections. This one happens to be the E-grouping section. This one's the runoff length section, and there's other sections as well further down. Now, the important part about these two sections is they are actually pointing to external files. One is a radius table file, and the other one is a radiant gradient or relative gradient table file. Now, this E-grouping, these settings come from an old superelevation tool that we used to use way back when we had criteria. If you remember the word criteria, that's how old this technology is that this SEP file came from. It looked like from a dialog box. It looks like this, and this tool had a whole bunch of settings in it, and this tab happened to be the E-grouping tab, and you can kind of see the comparison of the settings up here and the settings listed here. And the same thing is true for the runoff length. There was a tab for runoff length, and these settings are very similar to this, and that's where this SEP file came from. It came from this tool that we used to have way back when. Now let's look at the first file that this SEP file uses. It's called a radius table. And here's a picture of a partial part of the radius table. You can see that it's broken out into whether it's a 4% 15 miles per hour, or we got 4% 20 miles per hour, and it just goes through all the design speeds for an R max of 4%. Now there's also an 8% section of the same file, and you can see this one happens to be 60 miles per hour, but there's also again settings for all the design speeds for the 8% max super. Now, these values come from AASHTO, and they are extracted from the table 3-8 and 3-10B, minimum radius for design superelevation rates. And they're extracted from a whole bunch of formulas and charts in the AASHTO Green Book 2011. They can be kind of long, those equations, especially for friction factor and stuff like that. And so we don't expect you to run or calculate these values. We just use the charts to calculate our superelevation rates, and that's what this tool is doing. Is it's using the values in those charts to calculate the superelevation rate based on the max superelevation rate and the design speed. AASHTO states the following about these numbers, though. When there's snow and ice are factors, test and experience shows that superelevation rate of 8% is a logical maximum, and that's why at MoDOT we use an 8% max, because we do get snow and ice at certain times of the year. Where traffic congestion acts to restrict top speeds, it is common practice to utilize the lower maximum, which in our case is the 4% max. And so that's why we have a 4% max table and an 8% max table in our standard plans. Again, 4% would be used in rural areas, because in rural areas, urban areas because there is traffic, and you don't want to be sitting on an 8% max super in a stop and go situation. They believe you could possibly slide down on the superelevation if you're in stop and go traffic on ice or snow. Now the relative gradient table is a little bit more complicated. It's a much smaller file, and if we look at it, it basically has this information in it, where we got the design speed across the top. We have an L-min, which is the minimum runoff length, and we'll talk more about that in a second. And then we got something called RG, which is relative gradient, and it's got its values here. Now the relative gradient is the slope of the edge of pavement relative to the axis of rotation. And we've got a couple of examples of that. We first look at our standard plans that we showed you just a few minutes ago. And the relative gradient is basically the slope of the edge of pavement, which is this is right here, this red line here. Also in this diagram, the slope of the edge of pavement could be this line right here as well. Okay, but we're going to focus on this edge of pavement, and it's the axis of rotation is this line here, and so it's the difference between this slope and that slope is the relative gradient. Now to show you this a couple different ways, we got some other visuals to show you. So if this is the axis of rotation, the center line, and this is the outside slope of the edge of pavement, if you look at a cross-section view of this, you can see that the axis of rotation is staying at the same elevation in this example here, and you can see that the outside slope of edge of pavement is actually going from a -2 to a 0, which is the CC section, BB section, and then at the CC section we're at 2% full super, and you can see that that elevation is getting higher as it goes through the sections from AA to BB to CC to DD, and so it's that slope of this profile of this edge of pavement relative to this slope at the center line. Again, to show you this in a different kind of view, say we have a 2% slope there, we have a 0% slope there, so we're actually at the BB section, not CC section, the BB section here. And if we would carry that purple shape with those slopes all the way through this, and we go down to this side where we're at full super, which is also known as the DD section, and if we look at that runoff length from the CC and from the BB section to the DD section, this is called runoff length. Now what we're doing is we're comparing this edge of pavement, which is equal to the slope at the center line, to this edge of pavement, which is going from this 0% all the way up to full super. We're comparing the difference between those two slopes, and that's called the relative gradient. Again, this is the BB section, not the CC section. The BB section is where you're at 2% on one side and 0% at the other. Where does the relative gradient numbers in the table come from? If we look back at AASHTO, the maximum relative gradient is varied with design speed to provide longer runoff lengths at higher speeds and shorter lengths at lower speeds. It goes on to say that for appearance and comfort, experience indicates that relative gradients of 0.78 and 0.35% provide an acceptable runoff length for design speeds of 15 and 80 miles per hour respectively. So what I underlined experience indicates because there's no equation in there for these numbers. They just come from best practices or experience over the years, and so they basically use these numbers to define for 15 and 80. They go on to state that interpolation between these values provide the maximum relative gradients shown in table 3-15. If we look at that table, you can see the maximum relative gradients, and you'll notice that they match the relative gradients that we have in our file here. Okay, so what do the maximum relative gradients numbers mean? Let's take a look at a design speed of 30. We get an L-min of 36 and a relative gradient of 0.66. Relative gradient is just basically a rise over run formula. So if the relative gradient is 0.66, that equals a rise over run. If I assume a 1 foot rise, I can then calculate the run for that 1 foot rise. So if I rearrange the equation, it looks like that. And if I run the numbers, I get 151.8 0.5 feet for the run. So the relative gradient is a 1 foot rise and a 152 foot run. If I look at the table 3-15, you can see I got my 0.66 for 30 miles per hour, and then they also have something called an equivalent maximum relative slope, and that by chance just happens to match our 1 foot rise over a 152 run. So what is the L-min? L-min is the minimum length of runoff. And the minimum length of runoff will be based on the minimum superelevation rate you can have for a design speed, and that's going to be 2%. So if we look at the 60 miles per hour design speed, the L-min is 53 and the relative gradient is 0.45. So how do we calculate that? We use equation 3-23 from AASHTO to calculate the length of runoff. In this case, the minimum length of runoff based on the 2% maximum superelevation. This is the equation. LR is the minimum length of superelevation runoff. W is the width of one traffic lane, and we're going to use 12 foot for that. Number of lanes rotated, we'll use 1 for that as well. The design superelevation rate, in this case, we will use the design for 60 miles per hour. The adjustment factors for number of lanes rotated will be 1, and the maximum relative gradient in percent. Okay, so let's go ahead and plug in the numbers. Here's the equation in this format. Here's the values, and you can see the values that we're plugging in there. The lane width is 12, 1 lane rotated, superelevation rate of 2%. Again, we're trying to calculate the L minimum, and the L minimum is based on the minimum max superelevation rate, which is 2%. The lane adjustment is 1, and the max relative gradient is pulled from this chart here, 0.45. Minimum length of runoff is 53, and if we look at our chart, here is our minimum maximum superelevation rate for each design speed of 2%, which is the RC value. And if we look at 60 miles per hour that we used on the previous page, we should get 53 for 1 lane rotated. And that's what we have there. Now, in the chart we have a 1 lane and we have a 2 lane. 1 lane is 53, which we just calculated, but how do we get this 80 value? To get that 80 value, we have to look at the lane adjustment factors, and AASHTO has some information on that. A strict application of the maximum relative gradient criteria provides runoff lengths of 4-lane undivided roadways that are double, and those for 2-lane roadways, for those of 6-lane undivided roadways would be triple. So we just talked about how we calculate the maximum relative gradient. If you use that criteria word for word, again, you would have to double it for 4 lanes and triple it for 6 lanes. That's all they're basically saying. But AASHTO goes on to say that while lengths of this order may be considered desirable, it's not often practical to provide such lengths because those lengths get almost too long to design that. On a purely empirical basis, it is recommended that the minimum superelevation runoff lengths be adjusted downward to avoid excessive lengths for multi-lane roadways. So basically what they're saying here is based on experience, you need to avoid the excessive lengths by following the maximum relative gradient criteria strictly. You gotta reduce that down a little bit. And so they have some recommended adjustment factors in a table 3-16 in AASHTO. So if we look at this chart, it's right there on the right here, and then they've got some figures of roadways down below. So a 1 lane rotated is basically 1 lane on one side of the axis of rotation. If we look at 2 lanes rotated, there's 2 lanes on this side of the axis of rotation, and same thing for 3 lane. Okay? And so if we have those values, if we have a 2 lane or a 1 lane or 3 lane, you basically look at the number of lanes rotated and you use that adjustment factor. So here's some examples of lane adjustment factors. In this case, we have a median here, and we are the axis of rotation and the profiles being applied at this location on all these sections here. And so on this side, we have 2 lanes being rotated about the axis of rotation. Same thing on this side, we have 2 lanes rotated about the axis of rotation. And so in this case, it is a 2-lane rotated. Now if we change this up slightly, we have this now. Our axis of rotation is at the center line of the roadbed, and in this case, because we're rotating 1 lane about the center line, this would be only a 1-lane rotated. Even though we got 2 roadbeds, it's still a 1-lane rotated because we're rotating about the profile, which is at the center of the roadway. Okay, so to calculate this L2 value, what we do is we look at whether it's how many lanes are rotated. In this case, we're going to use a 2-lane rotated, and that's what this is right here. L means number of lanes rotated, 2 lanes. If we look at the value in the chart in AASHTO, 2 lanes rotated right here. Adjustment factor is 0.75, and so the length increase would be 1.5. And so if we look at the equation, L2 equals L1 times 1.5. L2 equals 53 times 1.5, and we get 79.5, and you round up to be more conservative, and that's where 80 comes from.